So we will move into the program. Normally, of course, we would do a round of introductions, but I think with this virtual setup, that's really challenging. So I'm sorry for that, but we will have to get familiar with the consortium throughout the presentations. So here we are with VIO, with our versatile emerging infectious disease observatory, an ambitious title and an ambitious project, as I would say. And I would like to start with this quote that I saw yesterday, that this is a situation where you're in a bar meeting with colleagues, with parents, dates, that's not my experience, and that is a quote from someone who works on sustainable learning and development in the workplace, and who is actually studying the impact of Zoom meetings on people's cognitive behavior. And it's not all positive, is what he concludes. So it is the challenge of working through projects like this with all these online meetings. There's actually a field of research developing around this, so that's interesting to see. But let's start with VIO. So why did we propose VIO? Well, obviously because of the emerging disease situation, likelihood of emerging diseases is increasing, and the likelihood of explosive spread is increasing in a time where we see that, and we have learned now very much the hard way, that preparedness for such kinds of outbreaks is limited. And looking at this landscape, zooming in on the observation that some of what drives disease emergence may, to a certain degree, be predictable and usable to develop earlier warning for disease outbreaks. Some degree of advanced warning, of course, would have or could have important implications. So this is looking into the One Health dimension, where this is a Gordian knot to reflect that the health of humans, animals, wildlife and livestock, and environment are tightly interconnected. And this whole system is what we share with pathogens. That's the little DNA here. Viruses, bacteria, and parasites, whatever, resistance genes, and that this system is pressured by changes in all these drivers. That's what this image reflects. So that therefore changes in one compartment here will also affect the other compartments. So this is to reflect the notion and the central philosophy of our project that if we want to work this through, we need to do that in an integrative way. Now, one of the key challenges to emerging diseases is, of course, that they seem unpredictable. And then that if you look at the front line, the clinicians, that should be the ones to really pick up unusual disease cases. For them, emerging diseases typically are really rare exceptions. Many clinicians will never see a rare zoonotic infection, for instance, in their lifetime. And the syndromes do not stand out. So it is a big challenge to really be prepared at the front line, and that's illustrated here. For instance, this is a list of notifiable diseases in the EU, which lists some of the infectious diseases for which there are public health prevention programs. And if you plot, for instance, the West Africa Ebola epidemic during its peak time, it still was less common than some of the most common targeted diseases that you look at from a public health perspective. And that is even much more striking if you go down to this list, where, for instance, here, COVID in March would have been very rare exception to the common clinical pattern that a clinician is faced with. And we've seen how challenging it has been, for instance, to detect the early incursions of COVID into Europe. And this is one of the reasons. So with VIO, we want to move a little bit to, well, into the ecology of disease emergence and say, because many of the emergent diseases come from the animal world, if we have a deeper understanding of what is happening here, including all the information that is already out there, can we maybe move to better preparedness. And in the key questions that we will be looking at, we have different perspectives from the, well, let's say technology, data technology side. How can already available data be looked at and mined to help us address some of these questions, but that needs to be done tightly interlinked with user perspective to make sure that we focus on the right questions, but also have this iterative process, as Istvan puts it, let the data speak and see what we can learn from that. And of course, there is big questions around what can and can you not do with data. We are facing new challenges, and how do we work through them? What is our responsibility as scientists? And these are important discussions that we also will be developing. There are lessons to be learned here. We build, of course, from the work done by Compare, but this is not Compare, it's a new project. We have new partners and we will work together to redefine where it is that we want to be going. And we, of course, collaborate with the sister projects Prepare and Recoded, that it also looks at data, but more from a clinical perspective. Data and the data sizes is a big part of the challenge, because we all are aware that there is lots and lots and lots of data, but of many different types, variability, different types of accessibility, and there's a lot to be done in, well, working to be able to even use data in a meaningful way. And then, of course, there is the issues about what you can and cannot do. This is just to show, Skip said this is not readable, and it's not meant to be, but just to show you there's a lot. So we have the data types in red that we were familiar with and worked a lot with through the Compare project, and for which we have developed basic data hubs for sharing and working with this type of data. But in VIO, we want to explore how to work with all sorts of additional other data types, and how does that interaction actually work. We will do that not random, but through scenarios, and we have 5 scenarios where the central word is change, to reflect that if you see change in drivers, that is when we need to start thinking about what that does to the likelihood of disease emergence. And the 5 scenarios are on a vector-borne disease, zoonotic wildlife-borne disease. We are witnessing one as we speak, of course. There's a climate change scenario, there's a silent epidemic scenario, and the disease X scenario, which of course we are also witnessing. And a lot of the work tomorrow will illustrate how we think to work with these scenarios to start our data mining questions. So if I need to give a one-page summary, so the key is that for each of these emergence scenarios, we will ask what are key drivers, what are possible sources of data that is already out there that can help us inform on those drivers, and what can we do with the data? How good is it? Is it accessible? And what is the process of moving about that to access, curate, and mine the already available data to address our key questions. And those key questions have been or are being defined for each of the scenarios. And here we do combine sort of the dry data and the lab data for additional challenge. This is the image of the consortium. So we're well spread over Europe, maybe a little bit weak on the Eastern European side, but a good consortium with a large geographic span, that's for sure. And a reminder that we do work, continue to work on the principles that were also there for compare. So interdisciplinary, versatile, building on established infrastructures that work across the EU, and that's really with the philosophy that we want to develop things that are there to stay, using fair principles and in agreement with the international regulations and for the highly diverse data types. So an example of, this is what the image that Frank Deger made. So here's the central nut and bolt of the project, which links the technology perspective. So let's say the people that work on infrastructure, data sharing environments, data connections, the users, the people that help shape and frame the key questions for each of the scenarios, and people that keep us linked to the what can we actually do, what are the ethical, legal, societal implications of what we're dreaming up here. And we have our external user stakeholder panel that we're still developing to watch over our shoulders as well, and to help to give us critical feedback on what we're trying to do. Of course, we were a little bit, we were starting in January, but of course that start has been taken over by COVID, where there's an illustration of the need for flexibility. For instance, for the people that model data, modeling these abrupt changes in contact patterns that were announced yesterday in the UK, where they actually did mention that the specifics of contact patterns that they don't want to see. So we see all sorts of abrupt changes that can impact on the disease spread that we see in Europe. And as Frank says, one very important aspect that we will also be looking into is what is actually the impact of COVID on some of the other diseases, and can we really see that throughout what we're trying to develop. So today's focus is on COVID, as a lot has been done. It is a Disease X scenario. In Disease X, we had this task, which we said, well, that would start somewhere in the third year. So saying, with whatever we are developing, we should, if there is a disease outbreak, we should bring that to the table. So that actually has been done, well, much earlier now, and that's what is being presented today. Of course, by default, this is not as much integrated as we would have it 3 years down the road, but I do think it's exciting to see how much actually has been done by the VIO consortium. I want to briefly mention that we have, as of recently, also two ethics advisors with Esther van Zimmern. I'm not sure if she actually is online, but if so, hello, Esther, and welcome, and thanks for doing this. And please keep us on our toes. And Peter Benenberg, of WHO, who is also very much involved in the Corona initiative, but who has also agreed to serve as our on our ethics board. So with that, by Marcel and Danielle on the infodemic as we've seen it in this epidemic. So Marcel, go ahead.
Sure. Can you hear me and can you see the screen?
Yes.
Yes. Very well.
Okay. So I want to talk about Twitter, but before I do that, I also want to explain why things have been a bit rough on my end in the past couple of weeks. I've been heavily involved in this digital proximity tracing for COVID, and in particular, I've been part of a group that's called DP3T, which stands for Decentralized Privacy Preserving Proximity Tracing. And this is in essence now what is in most smartphones, because Google and Apple, with their exposure notification API, which is now the API that most countries have committed to use, is using this technology. And so that's been a really interesting experience from so many angles. And I don't want to go into details here, but I want to mention that that this has also happened, and of course also with many amazing European partners. Good, then I'm going to switch here to this, and let's see if I can do this full screen without the thing crashing. This may or may not work. Let's see, does this work? I think it may work, right? Yeah, good. So some of you have seen these first two slides before, but I want to maybe briefly explain to you what we do in the Digital Epidemiology Lab with respect to this project, but also more broadly. We really like to work with Twitter data, and in some form of, I guess, cosmical joke, I actually started this line of work in the last pandemic during the 2009 H1N1, when social media slowly started to become a thing. I was really interested in vaccination and what the opinion formation on social networks about vaccination. And I looked into the H1N1 vaccine at the time as this was being developed. And I thought, you know, hey, there's this Twitter thing that everybody seems to be talking about. Let's get into this. So since then, we've been doing a lot of this work. And since we kept repeating this work again and again, you know, downloading Twitter data, analyzing Twitter data, visualizing Twitter data, eventually a couple of years ago, we said, you know, this is stupid, right? We're doing the same thing again and again with new interesting questions, but you know, we could do something slightly better. So we built this CrowdBreaks platform, which is open source at crowdbreaks.org. The code is open source, everything is open source. And so we're now using this, and if you've read the proposal, which I'm sure you all have in great detail, then you can see that's where we come in. So very briefly, it's a platform where we can easily get access to multiple Twitter streams for whichever purpose. We can then query that data. We can annotate that data. Either, you know, we do it ourselves, or we pay people, or we do it publicly, a sort of public annotation. That's completely open. And then we run machine learning models. We let machine learning models learn on the annotated data so that they can then go and do their thing. So annotate the data with machine learning on the non-annotated data. And that's very important because in the beginning when we started, we were able to annotate most of the data ourselves. And I mean 2009. Today, of course, this is completely impossible because we're getting millions of tweets per day. And even if we had hundreds of people annotating, we couldn't do this in real time. So we need to leverage machine learning, right? Natural language processing. But these algorithms are not good out of the box. We need to sort of, you know, like a human brain, very differently, but metaphorically, we need to sort of give them good instructions and we need to let them learn on how to do it. And we let them learn on annotated data. So we have been doing this in the beginning of this. Of course, when a new disease comes along, we very quickly get on it. And this was also the case with SARS-CoV-2. We started in early January mining Twitter for what at the time, you know, was called nCoV and Wuhan and, you know, all sorts of keywords. And then, of course, eventually we switched, we included SARS-CoV-2 and COVID-19 and so on. And we've since then been downloading 160 million tweets, of which we annotated, you know, over 10,000. And one of the first things we wanted to look at is what is actually the discussion about the worry, because that to us seemed like an important indicator, both in terms of news and personal accounts. And here you can see a bit of the data here, but this is still very much work, ongoing work. But you can see in the very early days, there was a lot of confusion. Of course, that also had to do with the fact that there wasn't too much data, but in the beginning, the worry was quite high, 5 being the maximum. And then over time, this sort of went further down. But of course, it will be very interesting to see what happens after March, when it really becomes clear that this is a huge outbreak, especially also in the US. So we'll be interested to look into this further. Just without going too much into the details, this is essentially how this works. The sort of most powerful natural language processing model these days is called BERT, and you know, it doesn't quite matter what it stands for, but it is a model that has been open sourced by Google. So it's really sort of the gold standard these days, but things are moving very rapidly. Already by the end of the year, it could be another model. But this BERT model is extremely, extremely powerful. But again, you sort of have to also tune it to become more powerful for the context that you're interested in. As you know, language is always very contextual. So we pre-train these models with Wikipedia data, mostly so that it becomes a bit more language aware of any specific language. So if we're interested in German language, you know, or Dutch, right? We take the Dutch Wikipedia basically as a corpora, text corpora, to sort of prepare BERT to understand Dutch, if you will. I mean, that's, you know, not quite putting it correctly, but we're training it on that language. And then we can do domain-specific pre-training, which in this case now, of course, is about COVID. And then together with the annotated data, we can get a final classifier for, again, for whatever interests us. So in the beginning, we were interested in, is this personal or non-personal? Is this expressing worry? What level of worry is this expressing? But we can come up with any classifier that we want, and I'd be very interested, you know, to hear from everyone in the consortium what they think and what they would need, what they would be interested in. But this is basically the process. So something else happened very recently, which was a huge deal for us, is that Twitter came knocking and said, hey, you people are doing good work. We know that. Many other labs are doing this as well. So we would actually like to give you and others more data with respect to COVID, because we rapidly realized we're running into you know, data issues from the Twitter side. Just so that you know, Twitter is generally very generic in what it gives you, but it does make a somewhat hard cut when it realizes that whatever you're querying you're querying an amount of data that's where they have to put a bit of a limit on it, and that is usually at 1%. So if whatever search you're doing, the amount of data that you're getting back is more than 1% of the total Twitter volume, then Twitter will put a break on your streaming. And of course, if you do something like Trump or now Black Lives Matter or whatever the thing is that currently gives volume, you very quickly run into this issue. And COVID, of course, was such and still is such a thing where you hit those limits. And so Twitter said, okay, we can give you more data, and we've been very grateful for that, and we're working on this. I can show you in a minute. But we're also now released this model that we trained this specific BERT model on COVID, and we made it publicly available. And I hope it's going to be used in many studies, and certainly we will use it for all the work that we will now do on COVID that analyzes text data, in particular also from Twitter. It's all open source, of course. We also provide this public annotation data set that divides tweets in either personal narrative or news. That's a very fundamental distinction if you want to analyze this kind of data. And again, here, this is what I mean. This is where Twitter came along and said, we can give you all the COVID data. There's no sub-sampling anymore. There's no quotas. There's a comprehensive keyword list for all languages, but it's not for everyone. So it did require a special admission process, but I'm glad we got through that and we got it. The only downside is it does not include historical data, and we're trying to figure out how we can fix that, because of course it will be incredibly useful to understand exactly what happened before May 5th. But that being said, as I said before, we were actually already collecting lots and lots of data since I think January 13th. So we were there since the early days, and I think we have most of the data, but there may be a time window somewhere between mid-March and beginning of May where we haven't gotten the full data, and we're trying to see what we can do about this. Of course, this is huge amounts of data. 1 month is now roughly 400 million tweets and about 3 terabytes uncompressed data. I know that geneticists among you are not impressed, but from a pure text data point of view, that's quite something. And yes, so this data is complete. So we can now also answer research questions which rely on data completeness, in particular also sort of, network structure analysis is always hard to do when you have only subsamples of the network. We know that from, of course, other network research. So it's great to actually have that data. Low resource languages is also something I think that will become more and more interesting, especially in a pandemic situation. And there it's great to have that. And again, no historical data, but we're looking on how to solve that. So currently we're focusing a bit on questions of what are the voices that are heard during this pandemic on Twitter, which is important. Who is listened to? I'm sure you can tell me stories of your countries, how that worked, and I think this is going to be a great reckoning, positively and negatively, about how these things unfold. And we're glad to now have the data for that, because a lot of it unfolded on Twitter. And who are the people? Are they experts in the field? Are they coming from the side? And how does this compare to pre-COVID times? But again, this is just one of the questions we can ask. We could really query this data for anything you want, and I'd be very interested to hear what you think. Last but not least, but this is where I will then hand over to Danielle, is of course all these questions about the network structure. And I don't want to really say too much about this, and rather hand over to Danielle, who's using the data there. So let me stop this. Okay, let me open the chat. Good. Good annotation is on a small fraction of the data. How do you know that that is representative? Yeah, that's a good question. That's also work we're looking into, but essentially we're we're initially trying to sample from just do random sampling. And then over time, we want to do something that's a little bit smarter. In addition, that we can do things that are more specific to certain question. Does it make sense to add other collected Twitter data from partners? Yes, I think so. In the sense that in the context where they could be interesting in terms of the question that is being asked, absolutely. So would be very interested to look into the data that's been collected from the mosquito work. The 1% rule with respect to analyzing Twitter data, that's really a Twitter rule. We haven't had access to any other data. We've been, personally, I've been a bit reluctant to look into other data sources, in particular data sources that are not public, because it puts you into all kinds of ethical difficulties. But it's something we could look into, and currently we're just focusing on Twitter. Structure the question from the consortium. You'd have to help me, Marion, how we want to do this. Maybe. Yeah, maybe we can set up a call of those people who would be interested to discuss these kinds of things. And then we have asked Twitter, I'll have to double check with Martin, but to the best of my knowledge, we have asked Twitter if we can share the data. And I think the answer was yes for inside the consortium, but I would have to double check on that. Yeah. I think that's roughly it. Oh, there's a question of a population, of a representative of the Twitter population. There, we generally tend to focus a little bit on the work that other people are doing in this regard, because it would be too much work for us. There are known biases, but the biases are also getting weaker as more and more people are using Twitter. But it's definitely something important to keep an eye on. What's interesting, of course, is that from what we're looking at here is that journalists, politicians, and scientists are very much into Twitter, and so that's sort of an interesting triangle when it comes to sort of understanding also the policy responses to this emerging outbreak.
Okay, great. I think we can shift to Danielle's presentation. So Danielle, go ahead. And someone is typing, so please mute your microphone when you're.
Do you see my slide?
Yes, it's not on presentation mode yet.
Yeah, no, I saw some question also from Marion about the undersampling, and I was doing a kind of metaphor with genomics data. Of course, if the distribution is very heterogeneous, as it is, the smallest events or communities will go unnoticed, but the largest events and information will be caught even in this undersampling. Moreover, as I will try to show quickly, some of the results we did are quite robust. For example, doing again the same analysis about 100 times, we obtain the same communities. If you do this with OTUs or other genomics data, this will not happen. So they look quite clean, at least. This is probably also due to the properties of social network, in which community are very much compartmentalized, and this is very, very different from biological species and compartments. So anyway, I will start with the presentation. So as Marcel,
to you and all presenters, briefly introduce yourself, because we haven't had this round of introductions.
Okay, so I am Daniel Remondini from a physics department in Bologna University in Italy. This is a work made in collaboration with my PhD Francesco Durazzi and the group of Marcel Salatin at EPFL that allowed us to access to this very interesting data. We deal with data analysis. We also do bioinformatics analysis, systems biology, and we apply a lot methods from network theory. So in this case, we were using network theory algorithms and approaches to characterize these social media data coming from Twitter, but we also hope to apply the same approaches to genomics data, and as we were saying, to the large set of data available through VIO, so be them environmental, climatological, mobility, and so on, hoping to integrate them in a clearer picture. So yeah, we were not supposed, at least in the beginning, we were not supposed to analyze social data, but when COVID outbreak and one of the partners of VIO proposed this very interesting data, we tried to do this analysis that I'm going to show you now. So let's go on. We wanted to characterize.
Danielle, can you put on presentation mode so it's a
Oh,
bit?
Yes. Okay. I didn't know how you were seeing it. Is it better now? Is it shared now?
Well, it's shared, but if you put it on presentation mode,
I did it in my computer. You don't see it as a presentation?
No.
Oh, that's bad. Why? Why is it?
For the full screen, we don't see the full screen. We see the presentation, but we don't see the full screen presentation.
Mostra, show.
There you go. Yep.
Is it okay? Oh.
Yes.
Okay, fine. So yeah, we wanted to characterize the Twitter network associated to coronavirus outbreak. As Marcel already explained, there are only tweets in English language. They were collected by the APFL group. And what we did, we tried to identify the top ranking users that will be the nodes of our network. And we try to define the community structure, so how these users were grouping within Twitter. We have links between users when they retweet tweets from other users. So we are mapping who is retweeting who. Okay. Starting from this network, we can characterize the main properties of this network, and particularly since they start from textual language, we did also some simple analysis looking at the main keywords associated to the communities. And as Marcel was saying, we would like to go to our more complex analysis about the meaning of the tweets analyzed so far. So we were starting from a set with about 80 million tweets in the period from January to April. We obtain a network with about 12 million users and 61 million links, because the tweets can be retweeted by the same user more time, so this increases the weight of the link. So what we did was to characterize the global distribution of the degree, so the number of retweets by the users, and we see that it is a highly heterogeneous distribution. So as it happens in social networks, you have some very big influencer and a lot of people, let's say, in the tails following this influencer, providing tweets and topics. As you see in the pie chart on the right, the top 60,000 users, over 12 million, contain about 87% of the total mass of tweets, and the remaining 13% for the other 12 million users. So you see that is very skewed and heterogeneous. So a very high biodiversity, as Frank was saying. What we did was to characterize the main communities. We identified 11 large communities, each with more than 10,000 users. And the first 11 communities were containing about 96% of the users. There are even smaller debris of communities that we did not consider. In order to identify these communities, as I was saying, we applied a common community structure algorithm more times, about 100 times. And what we get was that more than 99% of the same users were ending in the same communities. So this is why I mean it is rather robust. There is a very small overlap between communities. They are very much segregated within each other, and this is, I think, a typical feature of social networks, because we don't find such things in protein networks or in metagenomic community. On the right, there is a plot of this network and how the communities are close by for the top 60,000 users. You can see here on the left that this community share links. So there are tweets retweeted from one community to the other. Obviously, the plot doesn't say much, but it shows that there are different degrees of communication between communities. So we can identify which one are the most segregated or partially communicating, and this can be put in association with the messages within these communities. On the right, we show, for example, the clustering coefficient, which is a typical network measure that tells you how much intra communication there is within each community. And this also can be a description, one of the description about the properties of each social group, because different levels of intra-communication, for example, could characterize the different ways to diffuse the tweet within the community. So this is just a sketch of what we can observe here. Here are some examples. For example, one of the largest community, the second biggest one, that we call media, because it is very much fragmented in terms of countries involved in this community. There is 22% of US, some are unknown, Great Britain. But what we see in terms of the main keywords, on the right you see a word cloud. There were a lot of tweets coming from news agencies and also from WHO. So we could call this as a trusted community in which only true information is exchanged. In this community instead, which is one of the two communities we could refer to USA, because as you see, 3/4 of the tweets that were geolocalized come from that country, refer to message pro the US president, but there were also a lot of keywords associated to complot theories, like chemical weapons coming from Chinese lab. So we can think, but we have to confirm, that this is a cluster very much associated to the US region, but also to, let's say, fake news topics. Another community, for example, is clearly associated to the country of India, about 90% of the tweets, and most of the keywords refer to religious content. So they talk about meat consumption, they mention some gods and some concepts like worship. So you can see that this community describe different topics and different issues associated to coronavirus. What we would like to do, we have done, let's say, a static analysis, because we were considering all the tweets from January to April. And as Marcel was saying, there will be even more data coming. But we would like to split the whole analysis into different time windows, because maybe now we could be able to define a social outbreak, a peak situation in which there were the peaks of infection around the world, and possibly a late tail regarding COVID pandemics. And we would like to see if what we have observed at a global average level was maintained even in these different windows. Maybe users could have a different ranking, or the communities could split and merge, as shown in this plot. So this would give us also a dynamic idea about how people were thinking and talking about coronavirus pandemics throughout the world, at least the English-speaking world. And moreover, we hope, in combination with Marcel Group, to add more quantitative information about the content of the text through this, let's call it sentiment analysis, from the algorithm that they were developing and training, as he was showing a few minutes ago. So we hope to get a clearer picture of what was going on within this network and communities. It's very interesting, I think, for topics of public health. In general, it can be interesting because maybe you can do a lot of analogies or difference with other network-based models like biological networks. They look quite different, and probably this is exactly due to the causes that generate and construct these social networks and communities. And moreover, we hope to have feedback from the biological part of the project, also to identify possibly other questions or other specific analysis we can do on this data. Always related to social analysis, I will quickly introduce also a more classical, let's say, epidemiological model that we are doing on Italian, at least Northern Italy data, that anyway is related to social issues because it is related to human mobility. We got information about Northern Italy human mobility through mobile phones tracking by mobile phone private companies that gave us aggregated data regarding about 2,400 regions corresponding to zip codes, and we had hour by hour information about the fluxes of people in this northern region. So we implemented one of the thousands epidemiological models around. It is a modified SEIR model. So we had healthy, exposed, infected, and recovered people, but also with detail about who were hospitalized and who went intensive therapy. And we developed the mesoscopic model because we did not consider the global population, but different compartments corresponding to our zip codes. So we could add the information about the movement of possibly infected, healthy, and recovered people throughout these compartments. Moreover, even here, since we obtain a network of these 2,400 places in Northern Italy, we started to apply network analysis to identify the hotspots, the most followed path in terms of mobility that possibly could justify why there were peaks in infection in some regions and in others don't. And in principle, we could also be able to identify more isolated parts of the network or parts that could be easily isolated one from the other. So, for example, looking for future possible lockdown, maybe instead of a global lockdown, we could do it in a more localized way, just around the outbreaks, considering the most relevant route to human mobility associated, for example, to work, to school, and typical movement of the Italian community in this northern part of Italy. On the left, you see the most relevant direction. On the left part of the plot, you see the region around Milan, which is one of the biggest cities in the north of Italy. And some of the analysis show like this northern region is like a large metropolis, so it is hard to split it in separate parts. And also in size, it almost resembles the Wuhan region with about 10 million people, very tightly connected in a unique cluster. Even if on the right, you see a little bit through the colors that from left to right, there is the biggest degree of separation. You see from blue to red, the biggest distance between communities, maybe due to the fact that people work in their region or they do not move so far away typically, and so on. So we are trying to characterize the structure of this network and how this affects the model. So the added information by this, let's say, mesoscopic level of mobility, is it more informative than having just a big node encompassing the whole Italy or the whole regions of Italy? So we are trying to understand if this provides further useful information. And we will do it with network approaches by perturbing this mobility network and see how the global properties are affected. So how can we split the network into separated communities, which are the points that influence more the intra-communication. And moreover, a discussion we were having in the previous week, we would like to parallel this study with all the partners of VIO that want to join, that have similar data, so that we can also compare the different dynamics in different countries of Europe that maybe could have different size, different urbanistic feature, different habits, or maybe they are all equal, so we will identify some sort of universal behavior of epidemics in these highly urbanized countries as they are in most of Europe. Okay, so this is the end of my talk.
Great, Daniel. Showing just the power.
Specific topics, and for example, in identifying the different time windows, we should identify which could be the key events, or some yeah, that could be different from country to country. You saw that there was the India community and the US community. Probably they are not synchronized in terms of peaks, so maybe we should do something more stratified, and we need the more suggestion and feedback as possible. Absolutely. We still did not do that part because we don't have the knowledge about the main clinical, biological, and public health questions to be answered. So absolutely provide us all the hints that you think. So yeah, to link with pathogen genomic data. Yeah, of course, this would be very nice also, to combine different levels of information. This was one of the aims within VIO, so absolutely it would be very interesting.
There's a question from Nomzi Atama. What are the likely ethical issues with using such data? It's also a question, I think, for George and Carolina.
Yeah, for the phone data, I can say that, yeah, a colleague of mine is working with this mobile phone company, and of course, I cannot say we have the data. We make them questions, and they provide us answer to these questions following all the privacy requirements. So we don't have information about single cell phone users. We only have aggregated data, and we don't have the whole data, but only the data extracted for specific questions. So I don't know more than this, but for Twitter instead, there are the policies of the Twitter website. We also started using APIs to collect Italian Twitters in Italian language, and they provide you the way to extract this data with the limitation they were talking about, only a subset, no more than 1 week previews. But I think that if you download the data with their tools, in principle, you are not breaking any law. I think if they develop the tools respecting the rules, we are just using their tools. Okay, I don't know if you.
Yeah,
please.
I can maybe also say how we do this at CrowdBreaks. I mean, all the projects that we do with Twitter data are reviewed by the ethical review board here, and obviously approved. Otherwise, we wouldn't be doing them. There has been a debate in the field because initially, especially in the US, where most of this work was done originally, the stance was that this is microblogging, right? So it's public data in the sense that the user expects this to be public. and thus it does not fall under IRB purview. But then as it became more and more common, people said, wait. I mean, there are some specifics here that we need to discuss, and now there's some good guidelines around this. So, for example, we do not process any data that has been deleted, right? So when we process data and we use a single tweet, or let's say we want to annotate the tweet, well, if the user has in the meanwhile deleted that tweet, we are not annotating that tweet. And you know, also, like, you're not supposed to put you know, a tweet, for example, into a paper, because right, the user may have deleted that paper and may not have that tweet, and may not have given his or her consent for that tweet to go into the permanent record of that a scientific paper represents. So there are some guidelines there, but we're constantly working with our ethical review board, and of course also, as Danielle said, with you know, making sure that it's legal. But from an ethical perspective, it is constantly being reviewed.
Yeah, I can say, sorry.
So the question came from Nomzi, who is from the African region. Do you think there are regional aspects to this?
No, sorry.
I can't really say. Hello.
Yeah, go
Yeah,
ahead.
I was just curious about the ethical concerns as per individuals who are posting this data. What are the legal issues that may crop up if they decide to say, okay, this data was illegally used or something? So I did find out, but I think he gave an answer about the fact that ethical clearance is usually gotten before this kind of studies are conducted. So I think, and then also for data that are open source. So I think they're not bound by legal issues or such. So I think it's clear.
Okay,
Can I give a short
regional
comment, Marion?
Pretty sure. Yeah.
Can I give a short comment?
yes.
Well, I'm not really aware of the issues around Twitter data, but when it comes to mobile data, I know that at least in the Netherlands, we have to change, and we are in the process of this, change the telecom laws in the Netherlands. This is not so much an issue of processing the data, but it is an issue of that the telecom providers are very much limited in providing their data. So it might be especially a national issue.
Yeah, I have to say that we are quite new to this kind of social data. So we will ask for the help of Marcel not to do some naive errors. And up to now, this is just an internal document. When we will go towards a paper to be published, we will have to check that we don't do mistakes about privacy and about which data can be shown or not. So this is just for internal view at the moment, but we surely need to filter and do a better selection of what we can say or not. So maybe also George's group will be maybe relevant to characterize this. So
yeah, if I can, maybe, I mean, I think there's the two aspects are legal and ethical, and I think with ethical, it's important that everything we do, we run by our ethical well, you know, working groups, and but also the ethical review boards, obviously. And so far, in my experience in the past 10 years, this has been extremely cooperative and productive, and always resulted in a thumbs up. And the second part is the legal, where Twitter has clear guidelines what you're not allowed to do. So, for example, they have clear guidelines that you're not to extract a political leaning or things like that. So we looked relatively deeply into that, also because we want to understand, for example, what does somebody think about vaccines? And the question very quickly becomes, right, is that political and so on. That's where we're also currently in good exchange with Twitter on the legal side, right, that we're not doing something that's illegal.
So, but how do you deal with, I'm not sure if I understand it correctly, but the network node analysis that Danielle showed this brain of clusters, where Francesco says, so the two hemispheres are the Democrats and the Republicans. So if that's
for the US clusters, we see an almost significant polarization between two groups that seem to correspond also to political orientation. And it looks, but yeah, I would not write this maybe in a paper, that there is also some significant association to following, let's say, trusted rather than fake news. We are also working on this in Italy, so only with Italian tweets in Italian language. And here you clearly see the cluster associated to political movements. And yeah, I don't know how this can be presented, because you are saying statements that can have a clear political annotation, because every cluster is very much with names and surnames of people tweeting belonging to a certain political party. Some idea emerge very neatly. So yeah, I don't know how you can deal with it. I'm just looking at it as a researcher, but I don't know where you could publish also something like that, because it becomes in between politics and network analysis. I don't know.
Okay,
But
well,
surely Twitter,
I think we maybe should take this to the smaller group that we said that was going to discuss which questions to look at, but I do think it's extremely interesting.
I think just one point added, Marion. I think that it is very important in explaining these kind of positions of groups of people to know what is actually the bias of Twitter itself. So what is typically the group that is using the Twitter mechanism, and the question whether this is in what way is it yes or no representative group for example, the Democrats in America or the Republicans or things like that. And here there are a lot of questions, of course.
Yeah, it is not trivial, because also in biology there is a large bias. Some genes are studied much more because everybody knew them, they are associated to cancer and so on, and some other genes are less famous. So there is, yeah, I'm sure these biases exist, but yeah, this is the beauty and the problem of big data, that you can only deal with what you have. But surely this must be taken into account. I cannot state that this is the picture of Italy. That's the picture of Twitter users. Absolutely.
Exactly.
Okay, in view of time, well, it's obvious there's big work to be done here, very interesting. But I think in view of time, we should move on. Thanks both for this these challenging questions. And we move on to a session that we've dubbed Forecasting, Nowcasting, and Tracking, which also has an interesting series of talks. So, Luisa, floor is yours. Please start with introducing yourself briefly.
Hello to all of you. I'm Luisa Barzon from the Department of Molecular Medicine and the University of Padua. My collaborators, Enrico Lavezza and Stefano Topo, from the same department in the University of Padua, are also participants in this project, and they are participating also in this kickoff meeting. I will present a brief narrative overview on our experience with the COVID-19 epidemics in Italy. And as you all know, Italy paid the highest contribution in terms of disease and death in Europe and in the world, and it is still a top-ranking country as for number of cases and mortality, as all of you know. And we were the first country facing the COVID epidemics, and we had to face with this emergency. and we had to take many decisions that represented a model for other countries. So this is the outline of my presentation. So a brief overview on the epidemiology of COVID-19 in Italy, the public health response strategies, and an analysis of cases and contacts during the early phases of the epidemics, according also to the recommendation of WHO that asked the investigator to make some study to get an idea on the epidemiology and the clinical presentation of the cases. This slide represents the epidemic curve of COVID-19 in Italy, and each bar represents the daily number of COVID-19 cases that were reported in Italy. And I reported here the key events that occurred during this last few months, and also the decision, the important decision and control measure that were introduced in Italy. As you all know, on January the 30th, the WHO declared COVID-19 a public health emergency of international concern. And this led the Italian government to stop the direct flight from China and to declare a state of health emergency for a period of 6 months. And the next day, the first 2 cases of COVID-19 were identified in Chinese tourists, and a further case were identified in the following days, and also this case was related to travel, the history of travel to China. And the situation was quite quiet. In the following weeks, we had no further cases, while the news from China told that the situation was improving with the decline on the number of cases. But unexpectedly, on February the 20th, the first COVID case was reported in the Lombardy region, in the Lodi province, and this case had no relationship with China, with any travel outside from Italy. So it was considered an autochthonous case, and immediately contact traces was started, and this demonstrated that actually the number of cases was quite high. And the following day, the first 2 cases of COVID-19 were identified also in our region, in our reference laboratory for our region. Actually, we have a direct frontline experience with the COVID-19 as a reference laboratory for our region, and we performed a lot of testing during this period, and we were deeply involved in diagnostics, so maybe we hadn't so much time to do some research. Anyway, following the same day, the first case of death occurred, and it was one of the 2 cases identified in our lab. Immediately, the very important decision was taken, the lockdown of the red areas in the municipality involved in this epidemic, in Codogno and Vo Euganeo. And then I will later go into the details of what happened in our region. Anyway, this first analysis identified several asymptomatic infection or mild infection among contacts. So a no panic message was given to the population. And the same error actually was done also in other countries in the following weeks that had the same experience as in Italy. Then there was an exponential increase in the number of the cases, and an increase the first death occurred, and so this led to measure to reduce the epidemics. So the schools were closed nationally, and there was the lockdown in the northern regions, so Lombardy and the Veneto, but this led to movement of people from the north to the southern region of the country, like what happened in the one when immediately before with the announcement of the lockdown, when many people went outside the town. So immediately the following day there was a national lockdown, and the following days were quite dramatic, with an exponential increase in the number of cases and death that really challenged the public health system. and this led to new national restriction. On March the 27th, there was the peak in the number of deaths, approximately 1,000 cases of death in a single day. And this was the number of deaths and cases was higher than that reported in China. Then we could see the effect of the lockdown with a decrease in the number of COVID cases and the decrease of the number of patients that were hospitalized in intensive care units. So the government announced that after 1 month there would be an easing of the lockdown, and if the positive trend was maintained, the lockdown would end at the beginning of June, and this was actually what happened. This heat map represents the cumulative incidence of COVID-19 in Italy. Most of the cases were reported in the northern part of the country, where the southern part of the country was spared, relatively spared by the epidemics, and this was the consequence of the lockdown, or the national lockdown. And the two municipality, Codogno and Voi Euganeo, who had the first cases, are highlighted in the map. The cumulative number of infection is reported here, so this is actually this number not being updated with the last data for today. Anywhere we had over 230,000 cases of infection, about 12% occur in healthcare workers who, however, were diagnosed when they were asymptomatic or had mild infection because of screening. And so that is the reason why the mortality was lower among healthcare workers as compared to the general population, where the case fatality rate was really high, over 14%. And the high mortality that we experience is well represented in the picture there, showing military trucks carrying the people who died because of, so the victims of COVID-19 in the Bergamo town, who was one of the most affected towns in Italy. So now would like to present our experience with COVID-19 in our region. Actually, we had to face with in the front line the first cases of COVID-19 in Italy and the first case of death due to COVID-19 in Europe. This was on February the 21st, when the first two cases were diagnosed in our lab. Both had severe pneumonia, and they had an epidemiological link, and both were resident in the Voi Euganeo municipality. And they reported symptoms about 10 days before. Immediately, the public health system started the contact tracing and screening of the people, and we immediately changed the organization of our lab. We start working 24 hours per day, 7 days per week, and we are still doing that since February the 21st. And this gave the picture of what actually was happening. So there were many other cases of infection. A third case with a severe pneumonia was diagnosed during the same night, and this patient was hospitalized in the intensive care unit of our university hospital. And he has a history of previous hospitalization in a hospital in the Venice province. And also this patient had symptoms more than 10 days before. During the night, the index case died. And then there was immediately the decision to lock down the Voi Euganeo municipality for 2 weeks, the closure of the hospital where the two patients were hospitalized, and the decision to screen all the population in the Voi Euganeo municipality, that included over 3,000 people, and all the people and the healthcare workers who were at that moment in the hospital so where the patients were hospitalized. So all these people couldn't go outside the hospital without having the results of the screening performed in their nasopharyngeal swab. So we had to work very hard during the first hour of this epidemic to do a lot of testing. And this led to have a picture of the distribution of the entity of the problem. So 3% of the population in the Vaud Ghanaian municipality appeared to be positive at the molecular testing, and we had also an idea of the severity of the disease. 26% of these people were hospitalized, and out of these, 24% had a severe disease. But about 40% were asymptomatic, and they reported symptoms since the beginning of February. We also performed the screening among the healthcare workers and the people in the hospital, and also among these these people, we identified several asymptomatic infections, all with an epidemiological link with case. During that period, there was festivals, there was the Venice Carnival, and several gathering events for the population, and an important decision was made by the regional government and also by the national government to close all these events in order to prevent the spread of the epidemic. And the following days, contact tracing allow rapidly to identify different clusters that were quite distributed in several parts of the region, so in other provinces, and several clusters occur in the hospitals, involve the healthcare workers who take care of patients with the infection. So the situation appeared to be relatively under control by the end of February and the early beginning of March. So also in our experience, positive communication was given, and some experts in the field also declared that COVID was like a mild flu. And this was actually a problem because people moved and probably also contributed to the spread of the infection, and led to a widespread community transmission that we could demonstrate early in March, and then during the course of March, with a lot of new cases, a lot of mortality that really challenged the public health system, our hospitals, and our ability to test all these cases. And during these periods, also, we focused on the most severe case of infection who were hospitalized, like it is the same experience in other hospitals in other regions in Italy. We had to face with the problem of the supply of the personal protective equipments, the pulmonary ventilators for the patients, the stress to the intensive care units, and the problems with the supply of laboratory reagents for testing. Anyway, during the early phase of this epidemic, with the screening of the Vaud Euganian population offered us the opportunity to get some information about the epidemiology and the clinical presentation of the disease. So Professor Crisanti had the idea to perform a second round of screening in the whole population to get some information on the effect of the lockdown in a closed community. And actually, the second survey demonstrated a decrease in the prevalence of the infection among the population, with only 8 new cases reported in the second round, and the demonstration that a lot of the affected individuals cleared the infection. We also confirmed that the rate of asymptomatic infection was relatively high, but that these individuals actually contributed to the transmission. We could calculate some epidemiological parameters like the secondary infection rate among the contacts, the serial interval of infection, and the effective reproduction number before the lockdown and after the lockdown. These were important information that guided the also public health decision. This is the epidemic curve in Veneto region that shows that actually some cases of infection, so some patients reported symptoms at the end of January. And the mathematical model estimated that probably the virus was already circulating in the area in the mid-January. So this epidemic curves also summarize the key event in the Veneto region. So the first case is when they were diagnosed on February the 21, the first test related to COVID-19. Then the lockdown of the hospital and the municipality in Euganeo immediately, or school, churches, museum, and other social facilities were closed, as well as the carnival in Venice. And then there was the total lockdown of the region on March the 8th and the following day at the national level. And this was followed by a decline in the number of cases. And here there is also the report of the cumulative number of cases. So we have a total of over 19,000 cases. The incidence was quite high, as you can see. More infection occurred in females than in males, but the mortality was significantly higher in males and females, as other series clearly reported, and elderly people with comorbidities were highly at risk of death, and the case fatality rate was about 10%, so it was quite high also in our experience. Anyway, it was lower than in other regions, for the example, the Lombardy, that, as you all know, it was highly affected by COVID-19. And we identify some strengths in the response strategies that were adopted in the region, that are the different component and can be also useful also for the VIO project, because the VIO project actually include all these, the development of tools for tracing, testing patients. So in our region, immediately after the first cases were reported, so since February the 22nd, we collaborated with the information technology of the region, and they developed a very powerful information surveillance system that was based on the real-time integration of all the results coming from the lab with the personal information of each citizen based on public administration records. And this allowed a rapid real-time identification of all the possible contacts, and this was very important for contact tracing, and also to model and monitor the evolution of the epidemics, either at the regional level, but also at the very local region, or at the level of the hospital and so forth. And the physicians, the public health workers, and all involved in the people involved in the management of the epidemics have different level of accessibility to all this information. Testing was another important part of the response strategies that was implemented in our region. So we are in a network with the other laboratory in the region. We were, of course, prepared, thanks also to the contribution and networking with the EVD LabNet from the CDC, with the VIO project. So we were prepared, ready for testing before the outbreak. We had the capacity and the ability to reshape the organization of our lab in order to scale up and increase the number of tests. And so far, we provided a total of 600,000 naropharyngeal swabs tests for about 5 million inhabitants of our region. That is really a high number of tests that we performed during these 100 days since the beginning of the outbreak. And then also the the regional public health system was at a good organization that and could provided a proper balance between hospitalization and home isolation and treatment of patients, and this was associated with a relatively low case fatality rate as compared with the other neighboring regions. So to conclude, we can say that based on this experience in the front line, proactive surveillance and tracing strategies are very important, together with the laboratory preparedness and capacity to rapidly scale up and to provide a timely and extensive testing so far as much as possible to rapidly track and isolate all the cases in order to avoid and prevent the occurrence of epidemics. And this, of course, is very important now that we have ended the lockdown, that we have closed our COVID-19 hospitals, and that we are in a new phase, but we should be, of course, ready to prevent any new cluster of cases that could evolve into an epidemic.
Okay, thank you very much. So I see a few questions. Can you have a look at the chat?
I'm trying.
Yeah, and I think one of the, so I think it's interesting to hear your experience. So what we have, of course, been discussing in the separate meetings is how we can use these experiences in different parts of Europe to, well, to help shape some of the VO specific questions, and we will continue to discuss that also when adding it with, when combining this type of data with the pathogen genomics with the mobility data, and we will come back to that. One specific question I had is, so you were like early in the European epidemic, so the extensive amount of lab testing that was possible in your region really wasn't possible in other parts of Europe because of the market failure. And that's more a remark question, if that is information that from maybe trade data combined with simulations we could actually be looking into. If you know, if you rewind, could we have predicted this? Because that was a bit of a surprise, that the capacity to scale up really was impacted by, and in part driven by, decisions from big manufacturers of testing, rather than following the you know, the public health need. I don't think that maybe I don't think that's something we can easily address, but it would be interesting to explore.
Yes, it was based actually on the prediction model of the possible evolution of the epidemics. So since the epidemics in Italy started earlier than in other countries, with we actually ordered a lot of kits and reagents during the early phase of the epidemics, and this allowed us to survive during the period of when the bigger company could no longer supply reagents. So this is the reason why we were able to make all these tests during this period.
Well, and it's the same happened in Germany, and then the companies started to prioritize their shipments to the regions that already had cases. So that really, so they prioritized where the reagents went. It was not based on public health need, it was based on market.
Yeah.
You hear me?
Yes, and please introduce yourself.
Yeah,
briefly.
I'm Simon Cosmez, from Institut Pasteur in Paris. I'm leading the mathematical modeling of infectious disease unit. And I'm going to present work we've been doing to try to better assess the burden of SARS-CoV-2 in France. So we really started that as soon as the lockdown was implemented in France, and the questions we had was first to assess the impact of that lockdown, which was implemented on March 17th on SARS-CoV-2 transmission. Also, we wanted to make an assessment of the proportion of the French population that has been infected up to now, both at the national and regional level. And all that work was done in a context where there was a lot of needs from the Ministry of Health to try to anticipate what would be the needs in terms of ICU beds for the coming weeks. So that work was also done, like to try to anticipate these needs, bed occupancy to support planning throughout the lockdown, really. And the challenge is.
Simon, can you put on presentation mode?
Yeah, but like I'm on, if I do that, you will see, because I'm on multiple screens, so I'm not sure it's much better, right?
Oh, okay, no.
Yeah.
Okay.
So the kind of challenges we had to deal with was that, obviously, for example, if you want to make an assessment of the size of your epidemic, is that you just see really the tip of the iceberg. We have hospitalization data, we have deaths, but we know that there are a lot of cases that won't be detected by surveillance just because they are asymptomatic or they don't have severe symptoms. And so what we did to deal with that was really to do a joint analysis of the hospital surveillance data that is capturing severe cases, but then also other types of data that we can use to ascertain, like the unobserved part of the epidemic. And of course, the second challenge is that these epidemics have non-linear dynamics, and so we relied on mathematical models to capture these dynamics. So that's like a description of the different types of data we use for this assessment. First, as I said, the passive hospital surveillance, where we had more than 90,000 hospitalizations, and so these numbers now are a bit out of date, and 15,000 at the time, 15,000 hospital deaths, with a strong spatial structure, like Paris area and the east part of France were the most affected. So that's what you see on the left hand side, with you can see the patterns that you see in other parts of the world, where a strong gradient of hospitalization, ICU admissions, and death, with both age and gender. And so that is really what, like, again, the tip of the epidemic that we see. And then to reconstruct the missing, the unobserved part of the epidemic, we relied on surveys done in Princess Diamond cruise ship, where there was a big outbreak. All the passengers were tested, 700 were positive, and out of this there were 14 deaths, and also at the time 4 that were still in ICU and that we assume would die. And so these data on Princess Diamond can give us an idea of infection fatality ratios, and we can capture the fact that these infection fatality ratios will differ with the age of the people. And so basically integrating these two types of data, we were in a position to ascertain, like, the burden of SARS-CoV-2 infection in France. So here you can see the estimates of risks, so risk of being hospitalized if you're infected, of moving into ICU if you've been hospitalized, of death if you're hospitalized, and the infection fatality ratio for different age groups and different sexes and gender. And so you can see we estimate, for example, a probability of being hospitalized if infected of around 3.6%, with very important variations by gender and sex, and an infection fatality ratio which is around 0.7, with a confidence bound between 0.4 and 1%, and again always this very important gradient with age and gender, where male are 50% more likely to die than female infected persons. The other types of important features that we saw in the epidemic, and that was very important to explain some of the patterns in the data, was that over time the probability of moving to ICU when you're hospitalized changed and declined over time. And so it's likely there are a mix of phenomena that explain that. The clinicians say it's because they better understand how to care for their patients, and so they don't have to move them as often to ICU. But then it's also likely that there are other phenomena involved. The fact that the type of patients that moved to ICU, that were hospitalized, changed a bit over time. And so it's a mix of a lot of things. But so we account for that in our modeling, and then you can see here the reconstructed dynamics of so on the top it's the dynamics of ICU admissions over time in France. B would be the number of ICU beds over time. C, Delhi hospitalization admissions, and the number of general ward beds. And so these are these dynamics that we shared with the Ministry of Health to inform their planning, done both at the national and the regional level. And so we found that overall the lockdown reduced transmission by about 75–80%, from a reproduction number of about 2.9 to 0.6 of 0.7. We get the proportion. We estimate that the proportion of French people infected up to the end of the lockdown, the lockdown finished on May the 11th, was between 3 and 7%, depending on the value of the infection fatality ratio, with higher values between 7 and 16% for the most affected regions, Paris area and the east part of France. And as always in these models, we are making a number of assumptions about the contact rates in the different age groups, about also there can be the cruise data from the cruise ship that we use isn't perfect, because potentially population going into these cruise ships may be healthier than a typical French person. So maybe we should consider higher fatality ratios than in the cruise ship for France. It could also be that some cases were missed in the cruise ship. So there are a number. So we did a number of sensitivity analyses to see how our estimates would change depending on these assumptions. And for for example, if you look at sorry, it's a bit hard to see maybe for you, D is the proportion infected by May the 11th. You can see that for the different range of scenarios we can consider, we always end up with a proportion of French people infected that are below 10%. So just to conclude, here deliberately we only worked with hospital death. So we excluded the death in the homes for elderly people, and that was we did that because what we want to capture is immunity, is level of immunity in the general population, and the transmission dynamics in homes for elderly people will be very different than what we've seen in the community. So that's why we didn't account for this death. It's also possible that some there were non-hospital deaths associated with COVID, and in which case we would like underestimate the burden of infection in France. As I said, we relied on the cruise ship data, which remains relatively small, maybe healthier population, missed infection. So we accounted for, we explored like other scenarios accounting for these limitations in our sensitivity analysis, but it will be like very interesting to progressively integrate more data as they become available. And like for example, now we also have data from an aircraft carrier, Charles de Gaulle, where 70% of staff in the carrier were infected, and we get estimates of severity that are consistent with the Diamond Princess. And now we are doing the same kind of analysis, but more at a international level, so looking at similar types of hospitalization data by age in other countries to like reproduce that kind of work for other countries. Also starting to integrate serological data when they are available. And moving on to the post-lockdown situation, we are working on methods to try to quickly capture changes in transmission after the lockdown and performing short-term predictions with similar types of models. And I'll stop here. Thank you.
Okay, thank you, Simon. I say Simon. Do I offend you? Simon?
That's fine. No, that's okay.
Thanks. There's some question. I think, well, as we discussed, you've been heavily pulled into the public health response, but it's clear that there are interesting links in the follow-up of VO to be made. And part of your next step discussions are issues that also have been discussed in the silent epidemic scenario work that will be presented tomorrow. So I think we can link up there and see how to combine efforts there. So there are some questions.
Yeah, I'm trying to look at where to start.
There's some remarks and questions. So maybe at 11.1, Evelyn.
Wait, I don't have the. I'm on my iPad, so I'm sorry.
Oh, you have two screens and an iPad. That seems.
Yeah, it's a bit too much, maybe. Okay. 11. You said 11.
01.
11:01. Okay. Yeah, so the first question about do we have information about super spreading events in the French epidemic? I think that's like very important question, because in France, we initially had a number of clusters that we managed to investigate and contain quite well, and it looks like the big outbreak we have in Grand Est was really one super spreading event in a community that wasn't picked up early enough, and that potentially, led France to the situation it was in, where we really had no choice but to contain, because we then had a very explosive situation. And I think now that with the new system, the clusters are, I hope, and I expect much more better investigated than they used to be. So hopefully we'll have now like better data to investigate the role of super spreading events, but it's clearly, it looks like it's very important one for the SARS-CoV outbreak. So passive hospital surveillance, but like a question about active surveillance on positive cases. So that's like in the lockdown era, really we didn't, like testing wasn't done in a very systematic way because of a lack of capacity. And so now we are switching. So really, like for these assessments, we really relied on hospital data because that was the best data source. Now in the new system post-lockdown, we are going to rely much more on like the active surveillance on positive cases, and like using pathogen genomic data like would be that's something we are very interested in particular, like thinking about how this how it like it's still not clear how it started in Paris. So we have an idea about the Mulhouse outbreak, but then what happened in Paris is still not clear. So there are some there's real interest in linking with genomic data to try to better reconstruct the dynamics, like between regions.
Yeah, I think so. Maybe just to get in there, so we may be discussing this after the next two talks, but that's clearly a topic so we also discussed that with Louisa, where in different regions we actually may be looking into some of these super spreading event questions, looking on in the pathogen genomic data and mobility data. I think that would be a very interesting use of our capacities in this project.
Yeah, and I think that's all the questions for me.
Yeah, so there's some more, but I think in view of time, we have two more questions.
I mean, the others were like from Daniel, mapping possible pathogen host interactions on a large scale in terms of protein-protein interaction. I'm not sure that's for me.
So no, I think we can take the other questions later.
You can see my screen. Here we go. I hope I'm now showing it on full screen. So I am Sam Lysett from the Roslin Institute, University of Edinburgh, and this talk is some work about the genome sequences done with me and Lulu, and we are working on work package 6 and 9. So a brief outline of the talk. So we'll talk about the sequence data, some accumulation of the mutations, and I'll talk a bit about the timescale trees and tracing the paths using phylogenomics. So, as we all know, SARS-CoV-2, it's a coronavirus, and it's an RNA virus, and it has about 30 kb nucleotides. The sequence data from coronavirus is being shared on the GISAID platform, which I think has been spoken about before, but there are now well over 30,000 whole genome sequences. In fact, this is now more genome sequences than there are positions in the genome. The sequences are shared on GISAID, and it's actually the same system as influenza. You have to sign up to GISAID, but many countries actually deposit here first rather than GenBank. And on GISAID, this includes also the UK sequences, of which there are rather a lot. The in the UK, there's an amazing genomics consortium, and this is actually several places in the NHS and the universities and other places which are doing sequences. And at the moment, there are in excess of 20,000 sequences, and these have been deposited on GIS-8. In fact, these sequences also, certainly within the consortia, come with a lot more metadata as well. So where the, far more finer spatial detail of where the patients are, and also some details about those patients. So, so this is the general picture overall of the sequences on GIS-8, and you can see that there's a lot of them coming from Europe. But in fact, actually, this is the UK sequences are representing over 50% of the global sequences. And you can see here also the timelines of the sequences as they are collected, and you'll see that there's over 10,000 from England alone, but also from there's also a few thousand from Wales and Scotland, and a lesser amount from Northern Ireland. In order to try to look globally, I think really you need to have a system for classifying the sequences, and one way you can do this is using a tool called Pangolin, which is made by Andrew Rambo and team, and this assigns the sequences into global lineages. In fact, the links there also are showing firstly the link to the tool, but secondly the link to the sequences globally as they are classified as well. So if we look at global lineages, and under this system they're classified into A's and B's lineages, and then subsequently subdivided. I'm only showing here the lineages classified to the first level, but actually they go down to like B 1.5.6 point something, and you can see actually that for Europe, for example, these are mostly the B lineages. Excuse me. Hang on. Where am I? Right. If we, as just been mentioned, there is a mutation rate or substitution rates rather, and this is slower than flu. We estimate it to be about 1 × 10⁻³ per site per year, so that's 1 site in 1,000 per year. Bear in mind that there are 30,000 sites, but you can see already now that since the start you're having this accumulation of mutations, and you do get a molecular clock signal. And this is actually good enough really to trace the paths of the epidemics using phylogenomics. If we look, for example, this is just early data. This is data only going to March. You can see, and this is a timescale tree now. You can see it coming out of Asia, and then multiple introductions into Europe, and some introductions to North America, and some Oceania. I think just earlier we were also talking about nucleotide changes and amino acid changes. So even on this early data, you can already see some amino acid changes. But what is important to notice about these is that although they look like they might be in an important genes, so there's some in the spike, there's some in the polymerase, the alpha-1ab, and there's some in alpha-8. These are associated to particular places. So in fact, although these amino acid changes are spreading, they might just be founder effects. So at the moment, if you just look in the population, in the global circulating population, it's actually very difficult to distinguish between what's just a founder effect and is just spreading, but it's a founder effect, and what might be, you know, making a difference in, say, virulence or transmissibility. And I think to know that the different, you know, if the strains actually have different properties, then you really need to look to experimental studies. Looking now briefly at so we have timescale trees and locations. We can do the phylogeographic analysis, and so I did this for the early data, and I will just show this to you. Hopefully it will work. So I make the tree and I make it into a movie, and the dots are actually the ancestral node positions, and the blue patches are the uncertainties, but you can see the virus spreading out of Asia and over into America and Europe, and then now it's spreading out from Europe to other places again. And from these trees, you can kind of trace the path of the epidemic. So in fact, these trees are built assuming models, and these models also calculate the viral effective population size over time. So these models, there are, for example, an exponential growth rate coalescent model, which would give you an estimate of the growth rate. You can in fact use more sophisticated models to estimate, for example, R or R naught in different countries or continents. And you can also look at the changing parameters over time. So you potentially can look at the impact of interventions on phylogeny, because you'll see different clades growing or going extinct. And you can potentially analyze the epidemic by using these. So as a very brief example of this, we looked at some data from Germany actually, and on the left there you have a phylogenetic tree, and in the middle you have the derived effective R number from the phylogenetic tree. And what you can see is the viral population size giving the effective R number, but you can see that at the lockdown point that it kind of changes and goes below 1, so you can actually detect the effect of the interventions on the tree. However, we now have a lot of sequences. In fact, we have so many sequences and so many questions we'd like to ask, and you definitely cannot put all 30,000 sequences in BEAST, which is the program we use to do the very detailed timescale modeling at once. The upper limit for BEAST is about 1,000 really. So if you want to do a global analysis, we're now thinking, well, actually what you want to do really is you need to subsample to around a few thousand. But when you subsample, you should be subsampling by country, by week, and also by lineage, so you get a good representation of what's happening. And you can use more approximate methods. So you can calculate a maximum likelihood tree and put the time scale on afterwards. You don't have to use full BEAST for this. But if you're looking within a country, then you can look at the country, and you can also pull out the close relatives from the global tree. And you can use the lineage classification and clade structure as a guide to help you do that. And then you can run BEAST on these smaller data sets. Now, even in the UK, there's, you know, the 20-odd thousand sequences, but we're also very interested in what happens. So, for example, what has happened in Edinburgh, and so it's possible to pull out, say, only the Edinburgh sequences, and then find the related sequences and look at, say, imports and exports directly to Edinburgh, clade growth within Edinburgh. But the other thing that you can do particularly is you can include traits with trees. So these could be discrete traits like age bands or discrete locations, or of course continuous locations like spatial coordinates. And ultimately what you're doing is you're calculating rates that, that describe how these traits are changing. But in fact, you can do more than this, because you can then say, well, what is it that is driving the change between these traits? So what is it that is driving that particular rate, say between place A and place B, to be actually that value? And for that, you can use a phylogenetic generalized linear model. And within this, you can actually include time-varying drivers. So you could include, say, like, for example, an airline network that was switched on up until lockdown and then switched off again afterwards, and then maybe switched on a little bit as lockdown was being eased. And the other thing that we can do with the sequences that have the right metadata is we can also look at factors that might be driving disease severity, and perhaps these are like age and gender can be built into this model. And we can also look what, for example, what is the effect in different countries of having different types of strategies, of intervention strategies. And all of this we can potentially see in the trees using the phylogenetic GLM models. So in conclusion, there are a lot of sequences, and to analyze them, you want to do a global analysis on the one hand, and then a country or lineage analysis on the other hand. And you can infer predictors and drivers from the phylogeny so that you can understand what happened. But also, once you have the drivers, then you can use these to predict what you think might happen via simulations in the future. Or even if we ease lockdowns and restrictions, what will happen, and perhaps it will help us indicate if we should be reapplying restrictions because we see the situation worsening again. So with that, I would like to thank you very much.
Yeah, it's okay with me. I can start.
Yeah. All right.
So my name is
so
Martin Beer.
On the session, which actually moves back to more to the sort of the original thinking of VIO on the human-animal interface. So Martin, go ahead.
Thank you very much. My name is Martin Beer. I'm working at the Friedrich Loeffler Institute on the island of Reims. I'm working package leader for working package 6 in VIO, which is also a zoonotic spillover interaction working package. So we were not aware in the beginning that there might be the pandemic during, or a pandemic during the meeting or during the project. But we used our knowledge here to look at the host range, and that I will concentrate the first animal trials we did here, and talking about one reservoir host model and also the livestock, because that's something we are here in the institute especially interested. So this is work where many people are involved. It's a lot of money at the end involved. It cannot be all paid by VIO. That's also clear, because it's all the BSL-3 stables, etc. And I will talk a little bit on the fruit bats, a short slide on ferrets, which might be also a reservoir host model. If we look at the mink outbreak and the high number of minks which are in China, for example, and especially the pigs and the chicken, because this is important livestock where we were afraid, and others also, that the virus might be transmitted. You see here a lot of names, so everybody was working together, and more or less in parallel, we did this animal experiments. And that was all done here. That's a picture of the island. So you see we have all type of facilities, including a level 4 animal, level 4 human. These studies were all done in the BSL-3 area for animals. So as I said, I will concentrate on what we did up to now. There's other experiments running at the moment, and after my talk, Bart will concentrate on animal models. There will be a little bit application on the ferrets, but I think this is also important because there's many groups doing the ferrets, and repeatability and other things, or different type of pathohistology is important. So our questions were, are important livestock animals susceptible? So we selected first pigs and chicken. I will start an experiment in 2 weeks with cattle to be also inoculated. We have here a fruit bat breeding colony with the Egyptian fruit bat. So we use that as a model for different diseases, and we also wanted to see if they can act like a reservoir host, because the original virus most likely comes out of bats. And as I said, we look at the ferret situation, because we have here also ferret breeding and own ferrets for the normally for the influenza studies, but we use that now for the SARS coronavirus. And I will start first with something which worried us, that if you look at the receptor usage and everything, there were predictions. And one of the predictions was the pig should be susceptible. There were a few reports for the SARS-1 virus that there might be transmission. And there's also now a paper out saying porcine cells can be infected. They use PK15, and they showed that there is no cytopathogenic effect, but a high titer in this cell. So at the end, it's pretty important to test the pig if it can be infected or not. We also repeated the in vitro tests, and we were pretty surprised. We could not infect the PK15, but we could infect the SK6 and the ST cell lines. This is a testis cell line. Both cell lines have a defect in the interferon system. I think this might be important. And they replicate the virus pretty well, nearly as good as the Vero E6, which are the in vitro model for replicating the virus, but there was no CPE. So the cells are happy, they are alive, and you get a really high titer out of it. So from the in vitro study, you would say, okay, pigs should be infected, and it should not be a problem of the receptor, as predicted. And therefore, to look at the study design, we had normally 9 animals where we took out at several days animals and 3 direct contacts. For the bats, for the ferrets, for the pigs, and for the chicken, we had 17. Because for the chicken, we also hatched them by ourselves. So we start with a larger number of eggs. And if there's more coming out, so 17 eggs were successful, then we have 17 animals in the trial, or 23 are the direct contacts. We used the Munich isolate. That was the first isolate in Germany. And we inoculated 10 to the 5th per animal. Intranasally for the chicken, we use a oculo-oronasally way, as we do for influenza also. For the pigs, I think this is important. We used a spray device to have a real aerosol which goes everywhere in the nose and even deeper into tracheal or even the bronchus. And only to get an impression that this is all work we did under level 3+ conditions. So this is the same suit more or less as we have in the level 4, and but we have an external device for 2 HEPA filters and an overpressure in the suit. And you see that the hand gloves are really thick, so it's sometimes not so easy to deal with smaller animals like the fruit bats. But it worked. Everything worked very well, and these fruit bats are really very nice animals. They want to hang around and wait for their food, so they are always very relaxed and very nice animals. This was the overall plan. So we had several days, day 4, day 8, and day 12, where we took 2 animals out for necropsy. And at day 21, we stopped the experiment. We took nasal swabs or nasal washings, and we took rectal swabs and tested that by PCR, virus isolation, and we took sera for the serology. And to sum up, which is pretty easy, the results for the swine and the chickens, There was no mortality and no clinical signs. There was no loss of body weight, and there was not a single sample of these animals PCR positive or positive in virus isolation, and they did even not seroconvert, which shows that you have to do the in vivo studies, because from the in vitro, you would have predicted there might be, especially in the pigs, it might be possible to infect them. What the reason is that they are not infected, we cannot say. It may be due to the cell cultures we use that the interferon system plays a role. For the chickens, I think there was no replication in embryo cells in embryonated eggs. So I think there's really also, as predicted, the receptor too different. But from this small number of animals and this experiment, we would conclude that neither chicken nor swine were susceptible. And there was a similar publication now out by the Chinese colleagues, which saw the same for pigs, for chicken, and for ducks. So I think this is good news for the possible spillover. And it's, I think, also a good work for science, and maybe also in vivo, what is the factors that the swine is so different? And can this be overcome? So we are still looking at swine populations, and if there is a direct contact, we should still check if that's really not possible. But in both experiments, China and here in our hands, it's not happening, which is good news. If you look at the fruit bats, also no mortality, no clinical signs, no loss of body weight, but there was oral virus shedding from day 2 to day 12. It starts pretty early that the virus goes up. So day 2, day 4 is always the day with the highest number of genome copies. This is per microliter, so there is really a lot in some of these animals. They shed it. There is a little bit fecal shedding, and one of the 3 contacts was infected. So I think they can be infected. Most of the animals shed virus, and they infect also direct contacts. So even if this is a phylogenetically far related bat species, there is some susceptibility. And this, for us, it was a conclusion that people working with bats outside should be careful, because there should be some danger to bring the virus into other bat populations. And there were now some remarks from the bat researchers worldwide that they gave some recommendations how to deal if you work with bats. They catch them, they ring them, and people who are infected might transfer the virus in a new reservoir, which I think is not a good idea. So I think it's important to know that this can work. The viral load here you see is mainly in the nasal conchae, and they had a little bit of rhinitis. There's very low levels in other organs, including the intestine. So it's like the mild cases in humans. It's really replicating in the upper respiratory tract. This is a major organ also in the bats for replication of this virus. And this is also confirmed by antigen staining and by in situ hybridization. So you can see these brown dots. This is antigen or RNA, and they had a mild to moderate rhinitis. So there's something going on. The virus is replicating, and you can stain antigen and RNA. So this is 100% matching with the swab sampling. If you look at the ferrets, again, no mortality, no clinical signs, no loss of body weight. They were happy. They were not eating and drinking at one day. We had the feeling, okay, this might be less on day 3, day 4. And they had also oral or nasal virus shedding from day 2 to day 12. There was a little bit fecal shedding, so similar to the bats, but more virus. And all direct contacts got infected, and the first one pretty early. So they were outside of the stable 24 hours when we infected, so it cannot be a spillover by the infection. They came later, 24 hours later, to these animals. So we are pretty sure that they were infected by the virus replication and shedding from the inoculated ferrets. And I think it matches also very well what is seen in the mink farms, that this virus can spread very well in ferrets, or probably in this whole family of the Mustelidae. And therefore, we have to have in mind that there is a lot of mink breeding and mink holding also in China. So it would be pretty interesting to have more data there. And there's a lot of virus shed, especially early after infection. And also here, the nasal conchae are really the major organ, and there is more or less nothing in the lung. We find a focus in the lung if we look for a long time, but that's nothing which is a real infection of the lung or the bronchus. It's really upper respiratory tract. And this is even nicer confirmed because there's more antigen, more virus, and there is this olfactorial epithelium, as discussed for the humans. This is also the epithelium which is infected in the ferrets. So it looks a little bit like the mild disease in humans, but they have a special organ, which is a very old organ to smell pheromones. This is the vomeronasal organ, and this is very much infected. So there is a lot of antigen and RNA. So this is also something we should have a closer look at in the future, because there's also nerves in it and so on. So it's a very special part. And the olfactory epithelium, I think this infection and the mild rhinitis can explain that they were not so hungry for 1 or 2 days. And this is also described for humans, that they cannot smell or taste for some time. So I think this could be explained by the infection of the olfactorium and the olfactory epithelium. So very nicely matching that. Most ferrets got nicely infected and shed for several days virus, even at high titers. Looking at the seroconversion, as I said, chicken and pigs did even not seroconvert, so zero replication. Here in the bats and the ferrets, you can see that the ferrets, for my feeling, if I compare it to the human data, react very similar. The indirect immunofluorescence is going up very fast from day 8 on, with high titers going up at the end higher than 1 to 8,000. And a little bit delayed comes up the serum neutralization. If you look at the bats, they really behave different. As always, bats are really, I think, lazy in their immune reaction. And the EFA titers and the neutralization titers are pretty similar. So they have a moderate to low reaction in their serology, and there is not this very fast going up of antibodies, which are at the beginning not neutralizing. So it could be an hint, I think, for a reservoir host function, that they can more easy deal with that and react in a more normal way. So no overreaction in the serology. I think an interesting finding with low animal numbers, so I think we will probably repeat that also for the serology. And we check this now with different ELISAs and specific antibodies, S1 specific antibodies, RBD, and so on, to see if there is also a difference in the reaction. So if I summarize, what we did up to now is that neither pigs nor chicken were susceptible. And we have this paradoxon with the porcine cell lines, which should be some research in the future. We have this transient replication in the upper respiratory tract in both the bats and the ferrets. And as I said, the bats probably have a general risk of being infected anthropozoonotically. So I hope that this did not happen, because we don't know how this would behave in, for example, European or other Asian bat colonies. And the ferrets, I think they are good, probably as a model for the upper respiratory tract. And we saw in the transmission, and this is a part which we especially did in VIO, that we sequenced all these transmission events and the viruses, and they were stable in the beginning, but some of the transmitted viruses showed minor sequence changes. So maybe we should also compare that with the mink data, if that is similar positions or not. It's mainly in the polymerase and one is in the S. So I think this is also than going into working package 3, for example. So final conclusions, ferret could be a model for mild infection, but also for possible reservoir hosts like or suspected hosts like the minks. The bats show a different level also from the serology. So I think they could be a reservoir host model if you want to answer some questions. We never saw any clinical signs, so that none of these animals can be a COVID-19 model. I think there we will hear more from Bart, what is really models with disease or pathological changes. And as I said, we are still interested in other livestock animals, so the cattle will be the next to do experiments. And with that, I thank you very much.
Great,
and I
Martin.
have to check the questions.
Yeah, there's some questions.
Oh.
Starting at 12:22.
12:22, there it is, yeah. I think there's a question if we are able to predict the host range. I think the receptor is only half the truth. So if the receptor is not matching, probably this prediction has some value. If the receptor is matching, it does not mean that you can infect this species in any case. So I would always wait for the real experimental inoculation. And the genetic differences, we have small animal numbers. This is all animals from some farm or breed here. So yes, therefore I was happy that, for example, the pigs in China and here, this is 2 experiments, both had the same outcome. So I think it's good to confirm such kind of experiments because it has some consequences. The pig cells is one question. I think there for me it's the interferon, and it's not single specific genomic lineages of the animals. So this is all not inbred animals. So it could be that we have picked up a natural resistant variant, but it's highly unlikely, for example, in the chicken or especially in the pigs, because that is outbred animals which show a high variation normally. So some animals should be react and be infected. So pigs and chicken, have you used other assays to see if they are non-neutralizing antibodies? Yes, we started that, and we see that the later antibodies are very well reacting with the receptor binding domain. And the early antibodies, we are just looking at S again, and especially also N, but this is not finished yet. You think we should set up wildlife surveillance? I think we should do that very specialized. So not a surveillance, a very broad surveillance, but there is indication that people had contact, or we also advise if a farmer is positive, we should check his animals. Also for cattle or even for the pigs. I would say at the moment, the most resistant is probably the birds. But even for pigs, I would have a short check if there is anything ongoing that we don't overlook something. The raccoon dogs is an experiment we are doing, but I cannot yet say anything about it. But that's something we also do. Any indication choice of virus isolate? Up to now, not. But we also thought about, and therefore the Chinese experiments and other groups, the experiments, this is, I think, a good indication that we at the moment don't see a big difference in the ferrets, for example, with different isolates. But we have now also another isolate, which is different from the one we used. And for some animal experiments, we have now additional control groups where we use other isolates, because I'm also interested. Could we survey other bat species other than Rosetus? I think yes, should be done if there's any indication, or if the samples are there anyway, I think it would make sense to have a look at.
Maybe on that,
questions.
I think this group looked into, so they screened the bat collection that we have from Zoonosis in the Night project and found no positive.
Yeah. But I think that would be pretty early. So I would expect that, and now it's good that the numbers of infected humans go down, because this also reduces the risk of further events. And I think all this Mustelide is interesting. All these animals, also the raccoon dogs. I saw a statistic that says 20 million minks and 12 or 13 million raccoon dogs, which are held in China for fur, which is really a lot of animals. So would be interesting to have data from there if there were any spillovers, or earlier than the outbreak. Is it really a intermediate host or not? So I think this kind of animal groups, these Mustelide and also the Canidae, I think should be a closer look. What we do here is we look a little bit in the cats. We have 2 positive cats, and 1 cat was in a BSL-3 unit in Hanover. So there we have a series of samples, and we do there also the sequencing. And what we do there at the moment is sequencing the cat and sequencing the group of, it was a care home with positive people. So we will compare the sequence. So where were the cat infected? Because this is not clear, because they obviously had stopped any transfer of people in the care home, but the cats could walk around. So
Martin, in our mink farm situation, there's now 8 positive. So there are sort of semi-wild cats that really they hang out there because they just get free food. So some groups of them have been tested, and several of them have been seropositive, and I think 1 virus positive. But so there's clearly also an interaction between the mink, the humans, the mink, and the cats there.
Yeah, that's an interesting situation. And the cats, obviously, they are normally healthy. The antibody screening is not easy. You cannot use, in our hands, we cannot use the indirect immunofluorescence. There's too much cross reactivity with the cat coronavirus, the FIP virus, obviously. So, but the S-ELISAs is working, and the neutralization test is working.
Thanks. Great. Thanks ever so much. So does everyone hear me and see my slides?
Yep.
Great. Okay, so I'll start. Yeah, so I'm going to present the European COVID-19 data platform. It's true to say that from my institute, the EMBL European Bioinformatics Institute, this has become one of the major areas of work over the last few months. A number of people on this call have been working as well towards it, and the Commission, the European Commission's been directly involved as well in some of the planning and the steering of exactly how we do this. And so thanks to everyone concerned. The Commission also is covering this, supporting it financially through a number of different projects, but including significantly and substantially the VIO project, and we're of course very grateful for that. So what I'm going to do is step through the platform, introduce it, highlight some of the things that are particularly relevant to VIO, and come back to try to wrap up the VIO part of this towards the end. So yeah, so we started really in earnest, actively working technically at the beginning of March on this. The first component that was visible to most users was what we call the COVID-19 data portal, and this came out on the 20th of April, and we were delighted that at very high levels, the president of the European Commission, no less, this was promoted by the EU. So the portal is the entry point into the system for most people. It's the place where publicly available data are presented and organized. There are links to tools, there are links to different functions, and links to all of the external bits of infrastructure that I'll cover in a moment. this is the entry point, but there are many other points as well, and I'll step through each of those. So really, what we wanted to do was to work with, as EMBL EBI, my institute, with Elixir, which is the European Coordinating Organization for Bioinformatics Data in Europe, the European Open Science Cloud, and the Commission to build a system that will be useful in the scientific response to COVID-19. The focus for the platform is really the molecular biology data side of that. But of course, that's only a small part of what needs to happen. And so the platform covers on this slide here, that this left-hand part. This is the platform. We have the portal. There are other components I'll describe. These deal with making data available for research purposes on the molecular biology side, and these link in through the Elixir coordinating infrastructure to different bits of national infrastructure, including for clinical epidemiological data, but also connect onwards through many different European research infrastructures that exist, such as biobank infrastructures, clinical trial repositories, imaging infrastructure, drug screening infrastructure, and so on. And so the platform does this part, and it tries to link and make other things connected, but it doesn't do all of these parts. It's really focusing on the research molecular biology data. It's an important part, but it's not the whole of the story. And then to enable all of this, we look to the European Open Science Cloud, and I think this platform will become very much a demonstrator for the European Open Science Cloud over the next few years. So very locally, though, of course, to build the different components, we are working already with other people. There are a number of direct partners, and these are coming from projects that have previously existed, in particular the COMPARE project. And so we're working with Erasmus, DTU, ELTE, RIVM, and the University Clinic Heidelberg, really to build out parts of them. We'll see some of these build out parts of the platform around the data hubs already. And over time, of course, further partners will join. I hope, and I'm pretty confident that this list would grow and would add more together, be able to add more functionality and more utility to the system. So the aim of the platform are to collect data from different sources, data of different types, and to make these data available in useful ways as rapidly as possible. We do allow data sets with different degrees of aggregation, validation, and completeness. So this isn't just to produce a compendium of state-of-the-art data sets. This is also to share the raw forms of data that are still under analysis, still under question, and every intermediate as well. So the aim is to make different stages of the data cycle available to people, really to enable the broadest possible research activities on those data. And of course, as a platform with all of these data sets, we hope to enable synergies between people, so to allow research communities to work together in more effective ways. So there are three components to the platform. The first one is the COVID-19 data portal. I've mentioned this already. This is the entry point for most people. It's a website. There's programmatic access as well. There'll be a download everything function soon too. The second component of the SARS-CoV-2 data hubs. These are a specific set of tools for people who are generating viral sequence data to be able to share those data, to manage those data, to validate data, to process, and to start to interpret those data. It's a system that allows people to work privately if they wish to, but then to push data publicly when the time comes. Then the third component is the Federated European Genome Phenome Archive. And so this is builds on existing infrastructure, the European Genome Phenome Archive, EGA, which is a database for controlled access to data that need to be restricted for the purposes of preserving the privacy of human research subjects. So that system exists already. It's a federation of two different nodes, one in EBI, one in Spain. And this program is to extend that network, and I'll come on to explain later on why we need to do that. But this houses the clinical, this houses the human genomics data, human sequence data, and other data sets derived from humans, particularly on the molecular biology front, but has some opportunity to capture clinical epidemiological data as well. So the kind of process that we're trying to support here is on the left, you have patients who are providing samples. In some cases, the data from those samples enters existing national health data infrastructure, databases within health systems, or databases within public health laboratories and agencies. So the data enter these national level systems. And then there is a flow of, for example, the omics data from the patient into the federated EGA that I just mentioned. There's a flow into the SARS-CoV-2 data hub. So this is for the viral sequence data, and that part of the context, the metadata that can be shared publicly associated with those sequences. And then I have dashed lines here to represent connections. In some cases, we won't be importing all of the data into these systems. However, the data need to be linked. So we'll be making these links and maintaining these connections so people can move between systems. So that's the sort of storage data management layer. And then this feeds the portal. All of this is integrated and made available in different ways to the broad research community. So I'm going to step through the 3 different components. The data portal is that entry point. It has reference data, specialist data sets from humans. It will, I trust, have data from animal studies, and certainly has data from the virus, and perhaps also related viruses, related coronaviruses as required. And it has, in addition to the data that it holds, it also has linked links to clinical and epidemiological data outside, as I described. So we launched on the 20th of April. The early versions are focused on data that we're already capturing through the different databases we run at EBI, sequence, structure, expression, and so on. But over time, we're extending this to data that are not organized yet into those databases. It links to different external resources that are doing different parts of the scientific response. Such as the Elixir catalog, which is a list of resources that are connected through Elixir. And then there are next steps. There's a roadmap that includes linking to data and to further data into tools. Just to look at the status at the moment, so these are figures from today, and I'm just comparing them to figures about a month ago. So we're seeing most of these numbers are going up. We have, for example, 72 or 73,000 different publications, including so these are publications in literature plus preprints on preprint servers, 73,000 of which are identifiably in some way connected to COVID-19. We have viral sequences, so assembled consensus sequence, and then we have raw viral data sets. And a particular focus has been the mobilization of raw data. So it's been good to see this number grow. And over around about a month, we've seen some substantial growth there. Protein records, structures, we now have some screens of compounds, expression studies, and so on. And there's more to be added here, and I'll come back to that. So go and have a look at the portal. It does many things. We're improving it. We have a 2-week release cycle where every 2 weeks we release a new set of functionalities, and the data are updated dynamically. So whenever new data appear, they're immediately in the system. So we've added some nice searchability of this, in this case, looking at protein results. Here looking at sequence data results. We have embedded literature searches now. We have renderings of protein structures, and then these are some of the links. And then on the roadmap over the next few months, we have some other functionalities. For example, adding target data. There are now a number of data sets that describe targets, and if they exist, sets of compounds and studies of compounds against those targets. They're both viral and human. We have already launched, actually, is a genome browser for browsing data, including variation data in the Ensembl system. That's not yet directly embedded within the portal, but it will be. And then we have, for example, a dashboard. This is a very early form of a dashboard to track sequence activity. And we see here, for example, the numbers coming in from the Netherlands and coming in from Denmark of raw data sets. So a really nice development, not originally in our plan, but it has been that individual nations wish to pull together their activities into national level portals that will be connected to the European portal. And so we saw yesterday the release of the Swedish version of this. And so what this serves to do is to provide a focus for national activities, provide some of the coordination of national studies that are going on, to provide support for users with their data management and their data flow into the central databases and into the data hubs, and to link to some of the central functions. But importantly, to provide an access for scientists within the nation to those things that are happening specifically within the country, and those bits of assistance they can access. And so here, for example, we have this is the Swedish portal. There are data sets in here that are not yet fully connected into the central system. For example, images, and some of the target data, I think, as well. So the second component, the SARS-CoV-2 data hubs. So these are tools to organize for countries or labs to organize their viral sequencing data, to run computational analysis and to share these data and ultimately to publish these data. The focus is on viral sequence and the contextual metadata. We operate across all sequencing platforms that are in use and all sequencing library methods, and we're providing very deep user support. One thing that this platform enables us to do is to provide very direct hands-on support to people via, for example, video link, or by writing scripts and bits of code to embed into existing systems. So this is an unusually deep level of support that we can offer. There are many different types of user, from public health agencies, hospitals, academics, the larger sequencing facilities as well. And it's important to point out that the whole of the platform is building on existing infrastructure, but in particular, the data hubs are building on the Compare data hub model that came out of the Compare project. Here's the link to the publication that came out towards the end of last year. The Compare data hub model built many of the tools that are now being reused, and that itself sits on top of the European Nucleotide Archive, which is another bit of more generalist infrastructure that's been repurposed. So all of this is building on things that will be sustained into the future and reusing rather than starting things again. There's much new technology, but a lot of the focus is on reusing and adapting. We aim to deliver fair data for global research communities, and next steps include greater data coverage and adding analytical workflows. So we're just beginning to roll out the first workflows into the system. So one of the things we've been able to add is a simplified data submission tool for users who wish to use the web and have a simple upload process. Released this in early form on the 4th of May, and it's been improved over time. I can just show to give you an idea of the simplicity of this, if I can just show this video. So users have a key, so we can identify them. We set them up with a key. They log into the system. And then the user's going over to the right there to pick up some files. They drag those and drop them. These files are just a FASTQ file, which is a data file, and a metadata file. So that's a simple spreadsheet that describes their data set. And we've helped them to produce that. The files are now being uploaded. Take a while to get across into the system. And then there's a chance to send a note. So usually the user of this would be in contact with the support team as well to help out with the preparation of the spreadsheet. So there may be a note to add. So they're adding a note. Yeah, and then submit, and then that transfers the files, and that's it. That's all the user has to do. The processing happens in the back end, and then down at the bottom here you have this is a list of all the data files that have already been uploaded into the system. So this is the kind of thing that we've been able to launch quite quickly, really to simplify that process of pushing data into the system. And oh, I've now just lost my. Okay, so so again, we're actively developing many things here, and I'm just want to show from some work from some of the partners that's in various stages of development. So this is from Jötvös in Hungary, from István's group, Kupplex visualization. So this is one of many visualizations that you can achieve through notebooks. So this is an environment that allows bioinformatics aware people to come in and program and fiddle with the system without having to build whole new software components. This is the Evergreen phylogenetics system that's emerging from the Danish Technical University. This is the tree of everything we've seen that we'll be deploying. This is the now almost in production, but almost to be rolled out, Jovian analysis workflow from RIVM and Erasmus, and some of these visualization components, we're just finalizing those. And then here we have a cohort browser. This is on the recoded side of the work to enable people to discover research cohorts of interest in COVID-19. And so then the third component of the platform is the Federated European Genome Phenome Archive. So this is the controlled, as I mentioned, the controlled access system for dealing with data from human research subjects that are sensitive. And in many cases, these data sets are not allowed to travel outside the national borders. Therefore, they have to be held locally. And what the federated EGA system allows is it allows nations and other groups locally to set up a local instance, a local node. But that node is set up using the same technology, the same infrastructure as all of the other nodes, and they can communicate. So they have the same, they share an accessioning scheme, they share data structures and search tools and so on. So wherever you are in the network, you can search for the thing you want. The system takes you to where you need to be to request approval for access, and you go through that process locally, but then you get the same technical interface into the data if and when you're granted access. And so this was a plan anyway for the European infrastructures to build out this federation, but the data platform, the COVID-19 data platform gives us the opportunity to accelerate this specifically for COVID-19. So we're going to see some more rapid installations of local nodes of EGA over the next few months. So just want to loop back to VIO, and so we're delighted that VIO is very strongly connected or involved in this, and obviously it plays a lot of what we've been working on in Compare, and we've now programmed for VIO are very synergistic or identical. We just have a very specific case we have to deal with, and we have to deal with it very quickly, and we need to support people to do that. But it's an opportunity to contribute to the response through the VIO project, but it's very much an opportunity to showcase VIO. What we're building is reusable for other things, and we really hope this will give a boost to the technical side of data management and data coordination for infectious disease with actually no extra effort, because what we need for COVID-19 it will be very similar for other things as well, certainly for the lower levels of data sharing and data management. So it gives us a chance to accelerate and deepen some of the tools and support that we're providing through VIO, and we can rapidly switch over to this because we have this ability to second people and move people around EBI that already have the right skills, and we can recruit significantly as well. So it's an opportunity to really bolster some of the ambitions and the dreams that we've had in this area very, very quickly. And so I leave it there, and I will be happy to take any questions. Perhaps there are some questions already. Yes. Okay.
Yes, you have some questions already.
Okay, what time do I start at? Is that 12?
17 past.
17 past, great, okay. Yeah, so, okay, so is there all links at national level for each of the countries? No, so what we're overall for the platform, what we're trying to do is put in place groups of people, national coordinators, so people who have who are able to speak for, or at least connect to the national infrastructure that exists, to understand the layout of the science, and also to access have some kind of political connection as well. So we're going through that process, and that's a lot of that is connected to the European Open Science Cloud and how it governs things. On the Data Hub side, we've got a very direct connection. We put out a call back in March to the member states of EMBL, which is effectively very similar to the member states of the European Union. And we invited people to the EMBL council delegates, but the representatives to link us to those activities in countries that needed the support. And we had a lot of contact, a lot of discussions, and they're ongoing from there. So there we have contacts through EMBL into the countries, and in many cases they've linked us through to the public health labs that are doing the sequencing, and the scientists that are the primary, or that are amongst the primary consumers of the service. What's more distant is the connection to the public health data, so the databases that exist already for clinical data or for epidemiological data, where this is kept behind firewalls. We're beginning to understand where this happens, how this happens in some countries, but not in all countries. Okay, so the next question, we may be able to use the combined genomic epimobility studies that we would develop as joint case studies. Yes.
Yeah, that was more a remark, Guy. We discussed that this morning when you had to step out, but we will follow up on that. So it is really, it's similar to the pilot study that we're discussing for the Dutch data, which has both the clinical and the public health and the sequencing. So it's a good test case to see how to actually link up data in a way that
yeah. So we'd really like to know how that's organized and how we can connect, and where compute can operate and what's allowed and what's not, and what's not allowed. Okay, so the next question, going back, let's just scroll me forwards. Okay, so Daniel's comment to Marion. Can we VO partners already access and test the data system with our own data in private mode? Yes. Yeah, so yes, you can. The way to do that is to request a data hub. We don't yet, one thing we're working on, we don't have it yet, is a system for people to just go online and request a data hub in the system. We don't have that yet. For the moment, it's an email to our help desk or to Nadeem, who I think is also on the call. I'll put the email address in the chat after we finish this session.
I responded to that in that ideally I think we should find some multi-partner or test cases where we have several partners combined, so that we also test the between partner things.
Yeah.
If we put it on VO, we should be testing the collaborative part as well.
Yeah. So okay. So but I read that question as own data in private mode with other partners. Okay.
Yeah. Okay. Yeah.
Yeah. Yeah. Oh no, absolutely. So one of the core functions is this sharing amongst a group of collaborators prior to publication, and that needs to be trialed and demonstrated. Yeah. Next question, Clara. Is the back end of the drag and drop tool now automated as a manual process? Asking because this will be a useful tool for less informatics experience. Sustainability. Yeah. So it's not. No, it's not. It uses some automated steps, but there's still some manual work on our side in there. And our plan is that we automate more quickly than users take up the offer of the service. And so far that's fine because we don't have so many users. We have people who are able to do the processing. Sustainability is really important, and we need to build that full automation. But as the automation comes online, that won't make any difference to we hope it won't make any difference to the users, because they'll see the same submission interface. Okay. So Marianne, we're doing that. Okay, so that's the previous thing, I think.
Yeah. So Frank wants to know, can we start sharing assemblies? Yeah.
Yeah. So when can we? So when can the data hub stop providing assemblies? I think is the question.
No, Guy. This is because we also see that internally that it takes up quite a lot of computing time to assemble the genomes, but also to map genomes and organize all the reads. We have also all these VCF files that different mappers put out. So it's really, that actually takes up more space and has cost a fortune to create if you're looking at these big metagenomic data sets. So I was just wondering if it would also be feasible to do that, or if when it comes to assemblies, whether it's only the assemblers done by you that will be shared in these data hubs.
Yeah, no. To store the assemblies, that's already possible. You can upload those already. VCF files, you can also upload those. There are some conditions about structure and how you reference the for VCF, how you report the reference and so on, but that's just detail. Abundance profiles, we don't have a structure for that yet, but we should talk about that. We have a way of supporting new data types very quickly. I imagine that's a table of some sort.
Yeah. Okay.
Yeah,
cool.
we're ready for many different data types.
Yeah. No, but I think that could be. I still think we'll need to learn to take advantage of that, because we have had 25 years of learning to deal with sequencing information. But I think that the other data types could be just as valuable in the future. Cool.
Yeah.
Cool.
Okay. So Thomas, our metadata curated to ensure some uniform spelling. At the moment, only very lightly. We have done some work on fixing country names, spellings, and so on, and doing some work on dates. But there's no, as yet, we don't have a program to do that. But it's possible we will be able to spend some. I mean, we have some people that can work on that. But the key thing here, and this comes back to the sustainability, is that we build the right system that captures that information correctly at source. The real opportunity here is for people to feed that in a structured way. For that to happen, you need to have very good tools, and you need to have people who are very aware of those tools and aware of standards and so on. So that's a sort of joint effort by the data provider and the data platform as well. And that's certainly something we're working on.
But Guy, have you let go of the GMI metadata standards?
No, I think the standard the data standard we're expecting is above. Well, it's minimal. So our minimal standard for the platform for SARS-CoV-2 is compliant with the GMI standard, I think.
Yeah, so that means there is already some degree of metadata standard.
Oh, there's standardization. So there's a set of fields that have to be provided, and in some of those fields there is some typing, so it's control over how you provide them. But in other fields there isn't. So if you choose to report your geography by reporting GPS coordinates, then you have to do it in a particular format, and we validate that, and the system will reject it if it doesn't comply. But a little bit of further curation could be to then look at those coordinates on a map and check that they actually make sense relative to where you think the data are coming from. So that's not something we've automated. If people choose to report based on a country name, then they can only choose the country name from a controlled list. So that bit's controlled and that's checked. But the next stage down, the region or the locality is not, or the town is not, that bit's not controlled. So it's sort of different degrees. We aim to be more controlled about things, but they get increasingly difficult, particularly checking locations.
Yeah. Well, I'm sure we can come up with a challenging pilot for you.
I'm sure you can. Good. Yes, I'm sure you can. Yeah. Okay, Nadine sent the email address. Evelyn, full support for testing of combined genomic. That is what is of key importance to us to ensure this integrated data sharing and access. Yes. Yeah. So it's the combination. The integration is the challenge, and this is very much something we're aware of. Okay, Geo Omnibus raw process would be very useful. Yep. So that's to Frank from Daniel. We aim to capture every stage. So if people put in raw data into the system, we would also be structuring and presenting the data we processed on that alongside the raw data. Some people may just send process data, but we try to push for raw data in all cases. Okay, Clara's commenting on the standard already integrated. Different, but it's compliant, I think. Yeah, Beltran, agree. Evelyn, we will gain knowledge in COVID. Yeah, okay. Great. I think that's all that. Yeah, I've got to the end. The comments.
Okay, yeah, great. So I think that's our last presentation for today.